Have you ever wondered about how gravity works and how things are different out there in the universe? How gravity acceleration works near a planet and things like orbits and satellites? Well, High Peak Education coming right at you today. Thanks very much for being here with me. So glad you're joining us and would like to perform an intuition video about that, helping you to understand how exactly gravity works. So what we have here is we have a model of the Earth with a rocket ship. Now, of course, this video is being recorded in the United States of America, so we have nice USA printed here on the rocket. Go America. Okay, so anyway, what we're going to do is we're going to plot a certain force, that is a gravity force, as a function of radius away from the Earth. And this force is going to be in sort of these arbitrary units. Now, we're not going to give this force any units yet, but we're always going to be tracking sort of the back of the spaceship here on this graph as a function of radius from the Earth. Now, if the spaceship starts at the surface of the Earth, and let's assume we're taking off here from, say, Tanzania, looks like kind of Central Africa or something, we're going to have this spaceship lift off from. If I click on the spaceship where it is, notice that at one Earth radius, it's at one of these force units. Now here's an interesting thing. Suppose the space shuttle blasts off and it goes to a distance of 2 Earth radii. Now listen to me carefully. 2 Earth radii would be the same thing as 1 Earth radius above Earth's surface. In other words, 2 Earth radii away from the center of the Earth. But that's why we have the notion of height above the ground versus radius from the center of the object. As we'll see, radius from the center of an object that has a gravity influence is really what matters the most. But let's go ahead and move this spaceship to 2 units away from the Earth. And what do you think it should be? Do you think it should be half, a fourth, some other number, maybe 1 over square root of 2? So we're going to be about 2 Earth radii away. And look at that. It's about 0.25 of those units. So it's actually a fourth of the gravity force that the spaceship had when it was at the surface of the Earth. What about when it's 3 Earth radii away from the center of the Earth? In other words, 2 Earth radii off the Earth's surface. Have a think about it. Okay, so hopefully you came up with that we have 1/9 of the force that was original. And that's exactly what we see here. That's about 0.11. And then how about 4 times as far away? So 4 times as far away should be 1/16. And 1/16 is about 0.06. When we draw a curve, and by the way, this doesn't just have to be exact Earth radii multiples. If we're at, say, I don't know, instead of 1 Earth radius, instead if we're at 1.5 Earth radii away, it's some intermediate value. It doesn't have to be whole numbers, but if we connect all these points with a curve, notice that this curve kind of looks like 1 over r squared. For those of you that have taken mathematics classes, if this was, let's say, the y-axis and this was the x-axis, this looks very similar to the curve 1 over x squared, the so-called inverse square function. Now, in fact, this property happens so often in physics, we give it a special name, and we call this the inverse square law. That many properties in physics, when they spread outward, they have their influence falling off as 1 over r squared. Now let's think about why that is. You can imagine all of the gravity force, in some sense, is concentrated at the Earth's center of mass. Well, when we move away from that, you can think of that gravity is still concentrated at the Earth's center of mass, but you're taking that same sort of gravity energy, whatever you want to call it, and you're spreading it out over bigger and bigger concentric spheres. So think about this. Even when we're at this 1.5 Earth radii from the center of the Earth, you could imagine there'd be sort of this imaginary sphere, like so, that this rocket ship sort of exists on right now. Well, think about this. If we're back at the sphere that is 2 Earth radii away, okay, so 2 Earth radii away, I remember from my geometry classes that the formula for the surface area of a sphere is 4 pi r squared. So if it's 4 pi r squared, we have double the radius as the original, so we have 4 times the surface area. So if you're taking the same gravity energy, if you will, and spreading it over 4 times the surface area, then the concentration of that gravity force is only going to be 1/4 as strong as it was at the Earth's surface. Likewise, if we move to 3 Earth radii away from the center of the Earth, we're spreading over a sphere that is 9 times the surface area, and so we get 1/9 of the original gravity force. And then if we're 4 times as far away as we originally were, we get 1/16, and so on. So the factor goes down the bottom of the fraction and we square it. Hence we have the notion of the inverse square law. Now, by the way, I alluded to many physics quantities behave like this. In fact, any physics force that acts as a field will obey the inverse square law. You could hopefully think of something like an electric field or a magnetic field, which you would study in later physics. Those behave according to the inverse square law. As you move away from a charge or a magnet source, you have this 1/r² dependence. But this also happens for the intensity of wave sources. So things like sound or light. So if you're 4 times as far away, let's say from a sound speaker, you're only getting 1/16 of the intensity compared to if you're just, say, 1 meter away. And how about a light bulb? Would work the same way. If you're looking at the, what we call the flux, or the power per area, which is sometimes called the radiant intensity, or the irradiance, but in any case, if you're 1 meter away from that light bulb, you receive a certain amount. But if you're 2 meters away, then you get 1/4 the radiant intensity. 3 times as far away, you get 1/9, and so on. Because as a point source, you could imagine the light bulb is spreading its light energy out in concentric spheres, just like a sound source would spread its energy out into concentric spheres. So be aware of this, that many quantities follow this notion of the inverse square law, and gravity does as well. Now, by the way, we haven't given any units in terms of our SI units of force, which we know to be newtons. So let's investigate gravity force and this inverse square law in a little more detail, and let's be now a little more quantitative. So now what I'm showing here is an additional example where we can be a little more quantitative, okay? So imagine we have 2 masses that are each the same mass, and we can control their mass, and we can control the distance they are away from one another. Now notice, these masses are quite large. In other words, they're both 4 billion kilograms, okay? And we can increment their masses up or down by whole numbers of billions of kilograms. So notice that if you want substantial gravity forces between these masses, notice that the masses have to be astronomical in size to have any significant gravity force. Now I say astronomical figuratively speaking because they must be very large masses, but I'm also talking literally because I'm talking about things that you would study in an astronomy class, things at least the size of large asteroids, But for sure, things like moons and planets and stars, and of course even things like black holes, have significant amounts of gravity force. But that's because they're so massive. So gravity force on its own, with typical size masses we encounter here on Earth, tends to be very small. Now notice these two objects have the same force on each of them, but they're in opposite directions. Notice that that's just a restatement of Newton's third law. Equal magnitude forces, opposite directions. Notice that the gravity forces are close to 120 newtons or so, between two masses each having 4 billion kilograms of mass. And they're separated by 3 kilometers, so that's 3,000 meters. Let's see what happens if we, let's say, double the mass of one of the masses. Okay, so look at that. Both of the forces doubled. That's kind of what you'd hopefully expect. You double one of the masses, they both double. Now think about this. It's not just the force of mass 1 on mass 2 doubles. Because of Newton's third law, both of these forces remain the same. So even if you have unequal sized masses, the forces between them are the same. So what that really means is the force of the Earth on the Moon is the same as the force of the Moon back on the Earth. Now that doesn't mean the accelerations are the same. Earth is, several hundred times more massive than the Moon, but what it does mean is that the forces are the same, but the accelerations can be very different. Okay, so keep that in mind. Now notice right here we're about 240 newtons or so. Let's see what happens if we can verify the inverse square law. Let's see if we can move these objects to 6 kilometers apart, and hopefully we'll get 1/4. So in this case it's going to be hopefully just under 60 newtons, because I think 60 newtons would be about 1/4 of 240 newtons. So let's see if we can do that. So we're going closer to 6 kilometers, and there it is. So it's about 60 newtons. Notice that to go from 3 kilometers to 6 kilometers, we get a decrease of 1/4. So radius, that is distance between the centers of the masses, matters a lot more for gravity force than does the masses themselves. Masses are linearly proportional to the gravity force, whereas distance between the centers of the object is proportional inversely to the square. That's why we have that 1/r squared dependence. Okay? So this is what we mean by gravity force and being a little more quantitative. Let's see if I can show one more example that, again, shows this along with the graph of what we were saying before. So now what I have shown here is real sort of Earth-sized masses that are separated by a small distance and a more realistic gravity force between objects that you might pick up in your hands here on Earth. Notice that each of these two objects is 5 kilograms. So we're talking, maybe like a bowling ball or something. So 2 bowling balls, let's say. And notice that they're separated by about 200 millimeters. So 200 millimeters is about 0.2 meters. So about 20 centimeters. So something like this. Okay. And notice that their gravity force right here looks like it's about 4.16 times 10 to the minus 8th, and that's newtons. Notice this is kilogram meters per second squared, so that's newtons. Notice that forces between Earth-sized masses are very, very small, if they're not astronomical in size. So let's see if we can verify what we were saying before. Let's now decrease the mass of mass 2, leaving mass 1 the same size. Let's see if we get half of what we had before. So let's make this 2.5 kilograms. And notice that we do get half. Notice that this curve has less of a slope compared to what it had before. Notice that at the 5 kilograms, it has sort of a larger slope. It still has that inverse square law dependence, but notice that it has less of a slope. It's still a 1 over r squared, but again, it has less of a slope. Notice that each of the forces became half the magnitude when you decreased this mass to half. Notice, what is F21? Well, that's the force coming from 2 on mass 1. Here is force F12. That's the force coming from mass 1 on mass 2. By the way, this is quite literally a field force. It's the first real field force we've studied in detail in this course, because in this course, most of the forces we've looked at are contact forces. Tension is when you actually touch a string, or friction is when you actually rub on a surface, or an applied force is when you actually push on a box, and so on and so forth. A field force does not require contact. It can happen through empty space. So gravity is indeed a field force. Okay, so let's leave these masses as is, and let's see if we can verify the inverse square law. So let's move these to 400 millimeters away from each other. Okay, so let's see if we can do that. Let's get to 400 millimeters. And hopefully you can see that indeed it is 1/4 of what we had before. And you saw, as I was moving the masses away from one another, you saw that the force was going down this curve as that 1 over r squared. Okay? So, this is what we mean by gravity force. Again, follows the inverse square law, in units of newtons, need objects that are of astronomical size to really have substantial gravity forces. Mass is linear, but then radius is proportional to the square, but the inverse square. Okay, so now that we have gravity force established, let's take a look at how gravity force can influence something that we might want to put into orbit. Because here's the idea. The whole notion of this chapter is that the gravity force is not necessarily a constant. Up to this point this semester, we've been assuming the acceleration due to gravity is just a constant. In fact, it's usually 9.8 meters per second squared near the surface of the Earth. And even if you're at the top of a tall mountain, it's pretty close to that. Turns out it'll be slightly less at the top of a small mountain, but that's only for very precise calculations. But with that said, we assume that gravity force does depend upon mass, because the greater the mass, the greater the gravity force, but we assume the gravity acceleration is just the same. But now we're saying that when the radius gets substantially larger from the center of the Earth, we can't make that assumption anymore. And so now we're looking at the universal gravity perspective. So now let's think about when we throw objects, in other words, projectiles, what happens when we take a look at them and possibly throwing projectiles with gravity force, and then also seeing if we can get objects into orbit. So what I have shown here is a clever little experiment. It was actually a thought experiment from Sir Isaac Newton himself. By the way, this chapter is sometimes called Newtonian Gravity because we're assuming that gravity is a force that we can define with a certain equation, and we're not talking about how gravity warps space and time, which is more the Einstein perspective. So we're leaving that for later study. But for now, if we're studying gravity from Sir Isaac Newton's perspective, here's an experiment, a thought experiment that Newton himself came up with. Okay? So as Newton studied these gravity forces, he was the one that realized that an object that's out in space falls towards a body in the same way that if you drop something on Earth, it falls towards the center of the Earth. And that was a key insight, because that was not necessarily obvious, especially back in the 1600s. So this thought experiment, Newton imagined, suppose you had a cannon on top of a very tall mountain and you started firing it. Would the gravity be such that there's a certain relationship between this path and essentially the path of the object, and that sort of thing. Now, it turns out, interestingly enough, what we're going to see is that the center of the Earth, that is the center of mass of the Earth, is still going to come into play here. When you fire an object, believe it or not, it's going to have a certain trajectory. Now, by the way, we know what that trajectory looks like from earlier in the semester. Okay, it's a parabola, as long as you assume roughly constant gravity acceleration. And if it's a parabola, the idea is that it's going to have that parabolic shape. But note that if you fire it off of a very tall mountain with a very large initial velocity, say 1 kilometer per second, so we're talking 1,000 meters per second, it could actually have a substantial parabola shape so that it moves over a certain sort of curved portion of the Earth. Such that if you were to draw sort of an oval here, you could imagine that there's an empty space, but then this center of mass of the Earth actually is part of one of the two special points of that oval. And I'll get to that in a second. I'm holding off the formal name for that. So let's go ahead and fire this cannon and see what this might look like. So notice there's the projectile. And again, you could follow and make this one full shape and sort of include the center of the Earth here as a special point. And then maybe there's another special point over here. But notice that the cannonball is going to crash into the Earth. Okay? So it still makes kind of this curved path, but the curved path has some of the Earth curving out of the way. Let's reload this cannon, and then let's maybe shoot this as, I don't know, 4 kilometers per second. Who knows? Is that going to be enough for it to escape Earth? Well, let's see what happens. So it goes quite a bit further, but it turns out that it still crashes into the Earth. Let's reload. Let's try one more time. I don't know, 6 kilometers per second. Now this is a little bit of sort of trial and error to some extent, but not really. Because it turns out there ends up being sort of a magic number. And this magic number is, did you notice that each of those other two trajectories, the center of the Earth was still at play? But it was not as skinny of an oval. That oval is now becoming more round, if you will. Okay? That magic number for Earth, now by the way, this is going to depend upon the mass of the Earth, the radius of the Earth, and various things. But if we fire this cannonball at about 7 kilometers per second, notice that it still crashes into the Earth, but let's reload. Let's try 8 kilometers per second. And notice the cannonball now just starts to orbit the Earth. So you could say this, that the cannonball orbiting the Earth is just like a cannonball that would fall towards Earth, but it just keeps falling around the Earth. So sometimes people say, especially a circular orbit, is just an object keeps falling around the Earth, but the Earth keeps curving away. Now, by the way, what about this 8 kilometers per second? This 8 kilometers per second is very close to the Earth's what we call escape velocity. The escape velocity is a velocity that, it turns out for Earth, it's a little bit more than 7 kilometers per second, is the escape velocity. And it turns out if we fired from the top of a tall mountain, this 8 kilometers per second is in circular motion. Notice that as this cannonball orbits in circular motion, it's in uniform circular motion. This cannonball, being that it's in uniform circular motion, has a constant tangential velocity, has a constant angular velocity, because it's all the same radius, and it also has a centripetal force. And the centripetal force is the net force, but the real force, the thing that's actually holding it in towards the center, is Earth's gravity force. Okay? So the Earth gravity force would equal to the centripetal force here. Now here's an interesting question. What if we fired the cannonball at 9 kilometers per second? Now by the way, clearly when the cannonball was going around the Earth in that circular motion path, the center of the Earth was involved. That's because the center of mass of the Earth was the center of the circle. But is the center of the Earth going to be involved again? It turns out in each of these projectiles it is, but now it's going to be the top point of 2 points like this, and we're going to have this interesting sort of oval shape. And this interesting oval shape is not a circle. The center of the Earth is 1 point, and then somewhere over here is another point. But notice what's going on. Do you see that the cannonball seems to move faster through the cannon and slower when it's further away? In fact, notice that when the cannonball is closer to the center of the Earth, the radius is less and the gravity force should be less. As a result, I think the centripetal force should be greater. Because why? Because, well, if you have a greater gravity force and you have a smaller radius, you should have a larger velocity to maintain that larger gravity force so we don't crash into the Earth. But notice when the radius is larger, it seems to me that the gravity force is less, so the centripetal force is less and the velocity is less. So notice that this is non-uniform circular motion. In fact, it's not even circular motion. This is a very special name. Hopefully you know what the name of this orbit is, and we call this an ellipse. Hopefully you've heard this before. An ellipse has two foci, and a focus is going to be right here at the center of the Earth and also right there. And notice this thing is not in uniform circular motion. Its velocity is greatest through the cannon, it's least when it's furthest away. We can also explain this in terms of energy and momentum. I'll explain those later. But let's think about what it means to be in circular motion versus an ellipse. So let's investigate some orbits in some more detail. Okay? So now what I have here is a model of a satellite that goes round the Earth. That is to say, this is not to scale, but it's meant to give you an idea of how orbits look. And let's start off with the simplest case we can think of, a circular orbit around the Earth. So this satellite should take a circular orbit around the Earth. Okay? So let's go ahead and start this up. And this is what we'd expect. Uniform circular motion of the satellite around the Earth. Now, by the way, there's generally two ways that satellites can do this. If the satellite, through force balance, parks itself over the equator, the satellite would rotate as the Earth rotates, and it would stay over the same point of the Earth the entire time. And that we call a geosynchronous Earth satellite. Geo meaning Earth, synchronous meaning same time. It's over the same point of the Earth at all times. Good examples of this would be, say, like a weather satellite or maybe even a spy satellite. A weather satellite's a good example because GOES satellite, GOES, is geostationary observing Earth satellites. Okay, so GOES has various numbers. The weather satellites that look at the clouds across, say, the eastern United States and western United States, they're over the equator and they take pictures tilted up towards the United States for constant periods of time. Okay, so that's one possibility. Another possibility of a satellite that goes around the Earth in a circular orbit would be a polar orbiting satellite. Now, polar orbiting satellites can usually orbit at a much smaller radius. It has to do, again, with force balance. You can go much faster if you had a smaller radius. But suffice it to say, if the Earth rotates like this, and the satellite continues to sweep over the poles, you could imagine that the satellite's going to basically make little strips of data. A polar orbiting satellite will not come over your location, but maybe a few times a day, depending upon how fast it orbits. But generally, it can be at a much higher resolution, because it's at a much lower radius to the Earth, much lower height. It can take much better pictures. So things that you often see like Google Earth images or images of things in the ocean or things like that, that's probably going to be a polar orbiting satellite. Okay, but here's the basic idea. We have this satellite that goes around the Earth, okay? And let's go ahead and take a look at its path. Notice that, not too surprisingly, it is a circle, okay? Now, real satellites don't have necessarily exactly perfect circles. In fact, real satellites are constantly being adjusted and so on so that their orbits are pretty close to circles. What about the velocity? What would you expect the direction to be? Well, hopefully you said it's constantly changing, and it should be tangent to the circle. And that's exactly what we see. This is a tangential linear velocity. What about the gravity force? What direction should it be? Well, I think it should be towards the center of the Earth. Because again, the gravity force is towards Earth's center of mass, and this thing is only directionally changing, so the gravity force is acting as the centripetal force. Notice the force of gravity on the satellite and the force of gravity on the Earth are both the same. So you may say, wait a minute, why doesn't Earth move? Because there's so many satellites out there. Well, Earth is extremely massive. Earth's mass is approximately 5.98 times 10 to the 24th kilograms. That's an enormous mass. As a result, it is very difficult to move the Earth. Okay? So that's the basic idea. Let's also put the grid on here so that you can see a little better. Notice that this is one satellite radius, and then here's a satellite radius. You can see we have a circular path. Now I have a question. What should happen if we increase the mass of the space station? Well, the idea is that, interestingly enough, it shouldn't actually affect things. Notice that if we have twice the mass of the space station, the period is unaffected. Now the gravity force is double. That's not surprising. We actually saw that before when we did the intuition about gravity force, inverse square law, and all that. The gravity force is double, but interestingly enough, the speed and thus the period of the motion is unchanged. And that's because if you work out the equations for gravity force and centripetal force, the mass actually cancels. So the speed of a orbiting satellite is independent of its own mass. Okay, let's go back to the mass of sort of the International Space Station, so to say. And let me go ahead and reset this for a second and have you think about what's the typical period, the time, let's say, for the International Space Station to orbit Earth. Okay, so I reset. I want to go back to here, and let's do velocity, gravity force, path, and grid. And let's go 3, 2, 1, and keep your eye on Earth minutes. So we're going to go one full rotation, and right around there, approximately. So notice that it's just over 90 minutes. And that's pretty typical. The International Space Station can certainly be seen from Earth at night if you look up for it and you know where it is. It can sometimes even be seen during the day. The International Space Station is in what we call a low Earth orbit. So it's in the very upper atmosphere where the density of the gas is very, very low. And the idea is that, so it's probably, several hundred kilometers off the Earth's surface. But the Earth's radius is several thousand kilometers. That is to say, the Earth radius is about 6,371 kilometers on average. Now listen to me, I say it's on average. Part of the reason it is believed that the Earth is liquefied inside is because as the Earth rotates, it is slightly depressed on its poles. Its equatorial radius is just a little bit slightly larger than its polar radius. So it turns out Earth is not a perfect sphere. Careful measurements of Earth seem to suggest that Earth is what we call an oblate spheroid, and that's just a fancy way of saying that it's not a perfect sphere, but usually we just approximate the Earth as a sphere, and we take an average radius, which is approximately maybe 6,371 kilometers or so. You can look that up. Now, with that in mind, we say if this is about 6,371 kilometers, this distance of, say, 200 to 500 kilometers is extremely small compared to that of Earth itself in its Earth's own radius. So the space station will only take about maybe 90 minutes, about an hour and a half to orbit Earth. Okay? And by the way, this is a model. So this model allows us to see things a little better. I can also change this nicely to scale. So this is what it looks like to scale. So to scale, can you see that as the space station orbits around the Earth, okay, notice that this distance here is extremely small compared to the radius of the Earth. Because this satellite is, again, in a low Earth orbit. Earth's atmosphere is not actually all that thick. Earth's atmosphere is only going to be, and people argue about this, maybe 100 to 500 kilometers tall for any substantial density. It's hard to note where the top of Earth's atmosphere is. But most of the mass of Earth's atmosphere, I mean, more than 90% of it is in the lowest 10 kilometers to the Earth, to the ground. So you don't have to get very high up off the Earth's surface to get into very low density air. Hence why you hike to the top of a tall mountain, the air density is quite a bit less. Okay, but that's kind of the idea. So let's go back to the model and let's see, what do you think would happen to this satellite if we, let's say, doubled the mass of the Earth? Well, first of all, should the gravity force double? I think so. But, interestingly enough, what should happen to the period this time? Okay, so it turns out we can work out the equation for what we call the orbit velocity. And the orbit velocity, believe it or not, is proportional to the square root of the mass of the thing that you're orbiting around. So if you double the mass of the Earth, you should have square root of 2 times larger velocity, and I think the period should be less. So notice we can't really increase the velocity of the satellite, but indeed the force does go up and the object would actually crash into the Earth. Okay, so that's exactly what we see. In fact, I haven't shown yet the Earth going around the Sun. Okay, so when the Earth goes around the Sun not in a perfect circle, but in nearly a perfect circle. And if you look closely, look at the grid, do you see that there's a little bit of wobble to the Sun? The Sun does have, it rotates on its own axis, it moves throughout the universe and so on. But notice that the Earth is a little bit closer to the Sun over here than it is over here. So when the Earth is closest to the Sun, we give that a special name. We call that perihelion. When the Earth is furthest from the Sun, we give that a special name. We call that aphelion. So at perihelion, the velocity is a little bit different than when we're at aphelion. You have to look very closely on this. But hopefully you realize that in order to go round the orbit, so let's start it right up there, okay? You'd expect that Earth's going to go around this orbit in about 365.26 days. So approximately a year and a quarter. So that every 4 years we get a so-called leap year. So let's see when we get close to this point up here. Let's see if I can pause it right around 365 days. Pretty close. But anyway, you get the idea. It's supposed to be about a year. Now, notice that even if we increase the mass of the Sun, I noticed that the gravity force on Earth also increases, and Earth would, if it couldn't change its velocity, it would just get closer and closer to the Sun. Okay? And notice that eventually over time, I think the Earth is even going to maybe even crash into the Sun. So one thing you notice is, now that I've increased the mass of the Sun, if the velocity is large enough that it can still stay in orbit, the Earth is not going to crash into the Sun, it'll just move around the Sun more quickly. That is to say, the velocity of orbit is proportional to the square root of the mass that you orbit around, in this case the Sun. Okay? And notice we're certainly not in even a nearly circular orbit as the Earth rotates, as the Earth revolves. I shouldn't say rotates. It doesn't rotate on an axis as the Earth revolves around the Sun. Okay, so let's clear this model. Let's put the parameters back on. But now let's look at the Earth and the Sun and the Moon. Now this is going to be kind of an interesting thing. What do you think the Moon's path around the Earth is going to be? Well, it's going to be a nearly circular path. It's going to be slightly elliptical. It's going to be slight oval. But notice that when the Moon goes around the Earth, as the Earth goes around the Sun, if you notice the path of the Moon, which is shown here in purple, it shows that cycloid path, which we've seen before in this class when we talked about rolling motion. That, at least from the Sun's perspective, if you consider the Sun sort of stationary here, the circulation of the Moon going around the Earth, but then the Earth going around the Moon, it's a cycloid that cycles around the Earth's path around the Sun. Okay? So it's kind of interesting things. So we get some really interesting geometries out there when it comes to orbital mechanics and it comes to astronomy itself. Okay? So there we go. Notice, look at the Moon's gravity force. You have to pause it and look carefully, but maybe like if we pause it, say right there, do you see that there's a very small gravity force on the Moon in compared to the Earth's gravity force between it and the Sun? Okay. In fact, if we do this to scale, let's look at the Earth going around the Sun. Notice when the Earth goes around the Sun, the object looks a lot smaller than the Sun itself. Okay? So the planet you really can't see, and the star you can barely see. Okay? I can maybe zoom in. And then again, you can see the star a little better than the planet, Earth. And now let's do Earth, Moon, and Sun. And again, now let's put the velocities on and the gravity forces, and let's look at the path. So it's hard to see, but it turns out that the Moon is going around the Earth, but it's so small of a change. You have to really zoom in. You can barely see kind of how these two velocities deviate from one another. But indeed, we're still getting that cycloid path of motion, okay? All right, so this is what we mean by orbiting. And let's investigate this notion of an elliptical orbit in some more detail. Hopefully you are familiar with an ellipse somewhere in your life. An ellipse can be drawn. You can do this at home if you have two pieces of string, two push pins, and a pen or a pencil. An ellipse is the set of all points in the plane which are equally distant from two other points. And those two other points, we usually just draw a line between them and label that as an axis. And each of those points is called a focus. The plural of focus is foci. And we can just draw the ellipse. Notice that this is what an ellipse looks like. It's kind of a very clever and fancy looking oval that has a very specific shape. And it's elongated. Notice that this larger axis we call the major axis, and then this shorter axis here we call the minor axis. Now, how is a circle different from an ellipse? A circle is just the set of all points that's equally distant from one point. So if those two foci just become one single point, that we just call the center. And the center of a circle, and then of course that pushpin distance is now just the same distance for both of those foci, but it's just the distance from the center, and that we just call the radius of the circle. So this is what we mean by circular orbit versus an elliptical orbit. Let's take a little more of a quantitative or mathematical look at ellipses. So what I'm showing here is hopefully something you've seen in a college algebra or a pre-calculus class, namely what an ellipse geometry looks like. So for an ellipse geometry, notice that r1 plus r2 is a constant, and r1 is the distance to the point from focus 1, r2 is the distance from this point of interest, wherever the orbiting object is, to focus 2. And notice that we can define these various quantities. A is the semi-major axis. That's the distance from the center to the end of the major axis. Notice B is the distance from the center to the end of the minor axis. So B is called the semi-minor axis. And lastly, C is the focal distance. That's from the center to one of the foci. Okay? We can modify A, B, C, and E here. Now what is E? E is going to be the eccentricity of the ellipse. By the way, one thing I should also note, R1 plus R2 is always equal to 2A. So R1 plus R2 is always the length of the major axis. Well, if this ellipse has no eccentricity, it's exactly a perfect circle. Notice that that's because the major axis and the minor axis are exactly the same length. In this case, 110 units. Let's maybe call it 110 kilometers, who knows. But if there is eccentricity, notice that suppose the major axis stays the same length, 110 kilometers. As we're increasing the eccentricity of the ellipse, notice what's happening. The minor axis is shrinking. The distance between the foci is increasing. And notice that the ellipse is getting more elongated. So this would be a highly elliptical ellipse, we sometimes say. So this is how these lengths go together. Now, by the way, there's actually all kinds of relationships amongst A, B, and C, and so on. So I think it's like A squared minus B squared equals C squared. It's not exactly the Pythagorean theorem, so to say, but there is a relationship amongst them. And I think that eccentricity is going to be C divided by A, if I'm not mistaken. Let's see if I can verify that. If I make the eccentricity 0.5, notice that C divided by A, that's 55 divided by 110 is the eccentricity. So eccentricity is a dimensionless quantity, but it's sort of like some dimensionless measure of how much of an ellipse do you really have. Okay, so this is what we mean by elliptical geometry. Let's investigate ellipses in just a little more detail with back to our cannonball, and then let's also talk about how this relates to orbits of planets and things like that. So here is our good old friend, the cannonball. We know now that this is an elliptical orbit and that the Earth is at one focus. What happens if we fire the cannonball, let's say, at a larger velocity, 11 kilometers per second? Well, notice it's clearly going to go further out into space, okay? But it turns out, if you fire this cannonball fast enough, the cannonball will still actually orbit Earth, okay? So I should be clear in saying something. Before I kind of misspoke. The escape velocity is a little bit more than 11 kilometers per second for Earth. But the circular orbital velocity for the object is going to depend upon the radius it is away from the center of the Earth. But that orbital velocity is going to be, again, greater than 7 kilometers per second, but less than 12 kilometers per second. Now notice it says at 11 kilometers per second, the cannonball will take about 2,350 minutes to orbit the Earth, or approximately 188 seconds in this simulation. So that is to say, it's going to take about 3 minutes to come back to this cannonball, to this cannon that we launched it. So we're still waiting for the cannonball. I don't think it's been 3 minutes yet. But if we wait long enough, I think the cannonball should reappear and make this very large ellipse. Okay? Again, the Earth center is still one of the foci. So, come on back, cannonball. We're all waiting for you whenever you're ready. Okay, so we haven't quite reached the escape speed of for Earth. And by the way, the escape speed does depend upon the mass of the thing you're trying to escape from, but again, it does not depend upon the mass of the thing that's trying to escape. At least the actual velocity to escape does not. The force, of course, does, because if you have a larger mass payload for your rocket, it requires a larger force to break free from Earth's gravity. That's clear. But the actual velocity you need to achieve is not any greater as it relates to the escape speed. Okay? So, we haven't quite reached the escape speed here, but let's see if this indeed is an elliptical orbit for this cannonball. So, I have faith that the cannonball will come back. I mean, this says here that the cannonball will come back, so let's see if it does. Maybe if I get better at posting videos here, I'll play some Jeopardy music to see if the cannonball actually comes back. So, let's wait for it. I'll take a drink of water, always a good idea for a nice intuition video. Hey, there it is! Look, you see the cannonball? It came back. Alright. Let me reload the cannon. Previously, when we had fired at the 8 kilometers per second, that was the circular orbit, if you recall. And we also showed 9 kilometers per second. Why don't we show 10 kilometers per second? Now, 10 kilometers per second is also going to be an elliptical orbit, but notice that it's going to take about 24 seconds in this simulation. So this elliptical orbit is going to be about, in reality, 294 minutes. Okay? So there's the cannonball. Okay? And again, it's moving fastest through the cannon, if it could sort of pass right through this cannon. It's moving slowest when it gets out here. Now, the idea is that we haven't reached the escape velocity yet. Okay? So the Earth's gravity will still keep this thing bound to an orbit. Now, by the way, bound is an important word because things that are in orbit are bound via gravity and via their gravitational potential energy to the object they orbit around. So let's go on up to 12 kilometers per second. If we fire that fast, notice that the cannonball will escape to space, never to return. And then, of course, anything larger than that, say 15 kilometers per second, certainly the cannonball also never comes back. Okay, so now I think we understand circular orbits, elliptical orbits a little more, and escape velocity. Let's now try to understand these elliptical orbits for the planets. So now what I have shown here is a simulation by Professor Walter Fend where I can select the various planets and one comet and look at how that planet orbits the sun. Okay? So Kepler's first law says the following to us. The orbit of each planet is an ellipse, and the sun is at one focus. Now if you just look here, it's a little hard to see, but I think the velocity of the planet's a little bit greater on the right-hand side of this diagram than on the left-hand side of this diagram. So this seems to suggest the planet's not in circular motion, that Ptolemy and people who came before Kepler and Tycho Brahe, I think my Danish colleagues would say Tycho Brahe, if I pronounce that correctly, all these planetary scientists during the Renaissance period figured out that these were elliptical orbits, okay? So, even people like Copernicus should be mentioned in there, Nicholas Copernicus. So let's look at elliptical orbit. So look at that. Hopefully you can see that this is an elliptical orbit, and the sun is at one focus. Let's draw in the axes. So notice, here we have the major axis horizontally. There's perihelion, where we're closest to the sun, aphelion, where we're furthest from the sun. And let's draw those connecting lines. So look, the sun is at one of the foci, and there's empty space at the other focus. Okay? Notice Mercury has a certain eccentricity, just over 0.2. So Mercury has definitely an elliptical orbit, not highly elliptical, but still elliptical. Let's have a look at our good old friend Earth. Now look at Earth. Earth has an elliptical orbit, but almost a perfectly circular orbit. Earth's eccentricity is only 0.017. Part of the reason Earth's seasons are the way they are is because of really the tilt of Earth's axis. Earth is not very different in its distance away, perihelion versus aphelion. Believe it or not, by the way, Earth is actually closer to the Sun, that is perihelion, in December, and Earth is actually further away from the Sun in June and July. So believe it or not, that's not what most strongly influences the seasons. It does affect northern hemisphere versus southern hemisphere summer winter temperatures a little bit, but not substantially. I mean, not so much to like its effect is much less than that of Earth's tilt. Okay, so hopefully many of you know that Earth is tilted towards the Sun in summer, northern hemisphere, let's say, and the tilt is about 23.5 degrees off the orbital plane. Okay, and that's the idea. By the way, notice that Earth's semi-major axis, that's the distance from the center here to one of these sides, is about 1 astronomical unit, 1 AU. Now hopefully you're familiar with this. 1 astronomical unit is a very common thing we often compare against. So 1 AU is about 93 million miles, approximately. Okay, you can convert that to kilometers. I think it's about 186,000 kilometers, if I'm not mistaken, something like that. But the idea is that 1 astronomical unit is often a common measurement in astronomy. And by the way, we often also compare things to Earth masses and Sun masses. So when we look at other stars or we look at other black holes or things, we say it's this many solar masses, some multiple. It's just a convenient way. So if we go back to Mercury, notice that Mercury has a semi-major axis of about 0.387 AU. So Mercury's only 38.7% the distance from the Sun that Earth is. Why don't we look at our good old friend Pluto? Now, there's lots of Facebook groups out there that say things like, when I was your age, Pluto was a planet. Of course, Pluto has been demoted because it was not gravitationally dominant in its own area. People like Neil deGrasse Tyson and other people have demoted Pluto, so thanks, Dr. Tyson. You know, Sheldon on The Big Bang Theory had some words for Dr. Tyson about this, but I digress. Anyway, notice Pluto has a highly elliptical orbit, so its eccentricity is 0.252. So, I mean, Pluto is quite a bit closer to the Sun at perihelion than aphelion, at least relatively speaking. Notice Pluto is on average about 39.7 astronomical units away from the Sun, so it's way out there. Okay, now let's have a look at one more object, namely Halley's Comet. So look at Halley's Comet when it orbits the Sun. When it's extremely far away, notice that it's moving very slow. When it gets close to the Sun, it moves very fast. Notice that the length of the semi-major axis is 17.9 astronomical units. Also notice that the foci are really, really far away from each other. The eccentricity of this orbit is 0.967. It's extremely elliptical. Very, very large eccentricity, very stretched out. So we're going to investigate this some more when we look at Kepler's second law, which we'll do right now. So now we look at Kepler's second law of planetary motion, which says that the line joining a planet to the Sun sweeps out equal areas and equal intervals of time. Now, by the way, equal areas, equal time can be related to physics, but Kepler was actually doing this geometrically. So Kepler was able to make very careful measurements on grid paper and very careful measurements with his telescope and so on. And the idea was that he was able to sort of work this out. And it's pretty amazing that he was able to do this. Later, Sir Isaac Newton verified Kepler's calculations using forces. So, equal areas, equal times was later shown to be another manifestation of the conservation of angular momentum. How do we know that? We'll take a look at the velocity of Mercury here. Notice that Mercury seems to be moving faster, closer to perihelion than aphelion. Notice that each of these sectors is about 1/10 of the period of Mercury's orbit. Notice that even if I change the area of these sectors, so if I change these to 2/10 of a period, notice that these are still equal areas and equal times, but notice that these are, when you're at a smaller distance away from the sun, you have to travel a greater angular velocity. But when you're a further distance from the sun, you travel a smaller angular velocity to get equal areas, equal times. Now let's look at the vector velocity. It should be tangent to the path, but the length of it, which is the magnitude of the velocity, which we know to be the speed, should be different. Look at this. I think at aphelion, the speed is least. At perihelion, the speed is greatest. So notice that this is certainly not uniform circular motion. Furthermore, you could imagine that when you are furthest from the sun at aphelion, like right there, that's when the kinetic energy is least. But you know what? That's when the potential energy is greatest. When you get close to the sun, the kinetic energy is greater, but what that means is the potential energy is less. So this is also conservation of energy. Now how about conservation of angular momentum? When you are far from the sun, the idea is that your radius is large and your angular velocity is small. But if your radius is large, your rotational inertia is large, because the rotational inertia of a point mass goes like mr squared. When you're close to the sun, the radius is small, so the rotational inertia is small, but the angular velocity is large. So it's just like an ice skater spinning, but when they get closer, they bring their arms in a little bit, and when they get further away, their arms go out and their angular velocity is less. So Kepler's second law of equal areas, equal times works just fine geometrically. We now know that conservation of mechanical energy and conservation of angular momentum explain it, particularly conservation of angular momentum. Let's take a look at Earth. Again, these sectors look very similar to each other. They're not exactly the same size, but clearly they are equal areas, equal times. Okay, let's look at Pluto. Again, when I was your age, Pluto was a planet. Look at this. Okay, again, equal areas, equal times. Changing the angular velocity, thus changing the radius away from the sun, and we have Kepler's second law. Okay, and finally, for the finale here, what about Halley's Comet? Look at that. We still have equal areas, equal times. But do you see why this is sometimes called the slingshot effect? Because when Halley's Comet moves around the sun, it slingshots extremely fast. Notice when Halley's Comet's way out here, 2/10 of a period is at an extremely large radius. So this piece of area is a very, very narrow slice of sort of a wedge. Whereas 2/10 of a period from this point to this point sweeps out a very large angle going around the sun. Okay? So the velocity gets really large as Halley's Comet rounds the sun. So remember, Halley's Comet only comes around every 75 years or so, something like that. And yeah, you can see the velocity changing here. It's only a few kilometers per second, but if you pause it when it's close to the sun, I mean, it was like a couple hundred kilometers per second. I mean, it's moving very fast. Okay, so let's just look at one more example to kind of finish off with some interesting geometries about orbits and things. So I want to thank PhET, that's Physics Education Technology, at the University of Colorado for some of these great simulations. I haven't probably given them their nice due, but they have a lot of cool simulations here. Now, some of these we've already seen. What does the sun and a planet look like? Well, it looks like an elliptical orbit, so that we've already seen. And then what does a sun, planet, and a moon look like? Again, this is pretty cool to look at, to see that cycloid and that trochoidal motion. But again, we've seen this before, and if you keep this running, you'll see that we definitely sketch out some pretty cool sort of polar graphs, if you will. For those of you that have studied calculus and have studied these polar graphs, these are pretty cool to look at. Okay, but if I reset this, now let's take a look at an interesting geometry we haven't seen. How about a sun, a planet, and a comet? So what does it look like for Earth to observe Halley's Comet? Notice that Earth is a nearly circular path, it's still elliptical, but notice that Halley's Comet, depending upon where Halley's Comet is in its orbit, can only be viewed at certain times or only certain distances away. Let's take a look at a binary star. Notice that a binary star has, planets moving around it. I mean, a binary star is going to actually have a nice rotation here, so kind of interesting. How about Trojan asteroids? So most of this is just kind of fun. Notice that these are asteroids rotating around the sun. Notice that they have slightly different radii, slightly different speeds, but again, they're all sort of rotating around this large star. 4-star ballet. Suppose you have 4 stars all about the same velocity and the same mass. They sort of rotate around each other, and they make some really interesting and some really beautiful patterns. You see that they continue to retrace their paths, and notice that they move fastest when they're closest to each other, when the gravity force is greatest, and they move slowest when they're furthest away. Cool. How about slingshot? Notice that when we slingshot, notice that we're going faster when we go around, say, an object like the sun, and if we move fast enough, we can maybe have an escape velocity. If we turn on, let's say, a burn, which is we let the rocket boosters go when we're far from the sun, and when we're far from the sun, you can imagine that the potential energy is large and the kinetic energy is small, but it's easier to escape because we have a smaller gravitational force. How about hyperbolics? What if you have several comets that move around the sun? Well, they're going to have slightly different orbits around the sun. Look at that. They produce these hyperbola-type curves, okay, with certain sort of axes like this. How about ellipses? So let's try this out. Notice that this is an ellipse with a small eccentricity. The blue here is an ellipse with a larger eccentricity, and green has the largest eccentricity. So you can see now why the periods of rotation of the planets are different, because they all have different elliptical orbits. But remember, the sun is the focus, is at the focus of all those elliptical orbits. And then lastly, this one's mostly just fun. It's called a double-double. So it turns out that the geometry of orbits and gravitational interactions is something of beauty if you actually do really sketch this all out. I want to thank you for your attention, and thank you for watching High Peak Education. Please smash that like button if you enjoy this content. Please subscribe to the channel to grow the channel. Please share this amongst your social networks. I look forward to seeing you in the next video, and I also look forward to reading your comments. Thank you.